So this is the second session, part of the session, today's session, October 13. And I would like to demonstrate kind of the naive experimental approach that I have developed over the years to Fourier analysis. So I think it would be nice to say we have a MATLAB on our computers. We can use it, and there is a routine called FFT. Why is it called FFT? Because it's the fast Fourier transform, or as they claim, the fastest Fourier transform in the West, implemented in a very smart way. And it allows you to put input signals. I mean, I don't do this, but you can throw in a vector, column vector, you get out a column vector of equal size. You can put a row vector, you get a row vector of equal size. You can insert a matrix, you get a matrix of the same format. There, you have to know, it says, oh, I'm receiving a collection of column vectors. So the FFT of a matrix is actually the FFT routine applied to a collection of column vectors. Whereas if you're giving an image to the routine, you would not like to do the FFT, but you would like to do the two-dimensional Fourier transform. So we will see also in a moment the difference between one and two-dimensional Fourier transform. And then you can make a number of observations and try to understand how these properties that you can check with in a few lines of MATLAB code with respect to the to the continuous case. So if I produce a random matrix, real or complex, 3 by 5, I can only apply it to a column vector of length 5, giving me a mapping from R5 into R3 or so. So we can check what happens if I either say, please apply the Fourier transform to this collection of column vectors. So you have individual mapping of columns of a matrix, and then you do a linear combination with coefficients from the vector R. That means R1 times the first column of the image under the Fourier transform. Or you're saying, no, I would like to do a linear combination first. So I'm computing a linear combination with coefficients from the vector R. And then you're applying the Fourier transform routine to the linear combination. So here I'm testing whether taking linear combinations before or after is making a difference. And as you see, the output is just the same up to numerical precision of the system. So we can be happy that the Fourier transform is just giving you it is a linear mapping. Now, the next thing is that we would say, what can you say about the Fourier transform matrix? So what is the matrix generating the original one? I should tell you, my standard size of is 480. Why? Because it's not like a pure power of 2, like 512, with a small number of divisors. For later applications, we will be happy to have a large number of proper divisors, which means our discrete group will have a lot of subgroups, so we will understand subgroups very well. So you see there are other concepts from algebra now in the game. And so if I want to understand what the Fourier transform is doing, I could do this. I could, for example, verify that the Fourier matrix has absolute values 1s everywhere. So this routine tells me, comp norm says, well, are the two vectors, maybe I'm showing you, if you take a vector u equals 1 to 5, 7 or so, comp norm of 3 times u with u prime or so. Is a routine, it says, I don't care about the format of a vector. Each of these vectors has 7 coordinates, but if I compare them in terms of size, this the first one is is 3 times as long, and if you take the difference of the normalized version of the first one taken as a column vector and the second one, you will get a difference of 0. So it's the same vector, but just in a different format or so. Maybe also, you know, of course, the commands. If I put A equals zeros of 5, then I have an empty matrix, and I insert into this 25 coordinates, which means, sorry, okay, 0 is, it was wrong. So A equals zeros, it should be zeros. Then it just tells me that I'm inserting 25 coordinates in the natural order, which means first column first, then second column, and so on. Now, I have also a rotation vector, which is cyclic rotation. So if I take x equal 1 to 5, and I do rotation of x by 1, I mean my right shift. So the 1 as a row vector here is moving to the second position, and everything which is dropping out is moving here. Now, I don't want to use plots at the moment, but I just want to show you this. Clearly, you can shift in the opposite direction, -2, but you can also shift by 4 units in this case, and you get the same result or so. Now, E5 would be the unit matrix of size 5. And if you apply this unit matrix, I'm not sure, I don't see my last line here. If I apply this rotation matrix, the rotation operation to this, I'm getting the matrix for the shift operator. So the shift operator is, of course, a linear operator. I mean the cyclic shift. It moves the first vector to the second position, the second to the third position, the last vector to the first position. So this is a matrix. And so if I take, and this is my test matrix of size 5, so it's exactly the matrix that we have seen, test matrix, yes, right? If I do this, I can ask, I mean, how can I recognize when a system, now a matrix, 5 by 5 matrix, is commuting with such a shift operators? Maybe I should check also what is the inverse of the right shift, and of course this is the left shift operator, so I'm showing it once more. And so a matrix is invariant with respect to cyclic shifts, so you can do cyclic shifts before or afterwards, well, if it has certain properties. So maybe we take the matrix A and multiply it from the left and from the right, and you see this is clearly a permutation, a cyclic shift on the columns. And in the other way here, you see that multiplying from the left is just an operation on the rows. So if you do now inverse of T1 with A with T1, you're seeing the deviation from a matrix which is invariant under shift operators. So what is happening here? So if you have a kind of a matrix representing an operator commuting with cyclic shift, you would have assumed that A with T1 is the same as T1 with A. Now that is of course the same as multiplying with the inverse of T1, then with A, then with T1 should be the same. So we have to look carefully how is the difference between the original matrix A and this conjugated version of A. And you see the one has moved from the left upper corner, I would say from the position 0, 0, MATLAB, of course, coordinate 1, 1, to the next position, which is 1 down and 1 to the right. But if you also watch what all the other guys are doing, they're all moving along the main diagonal. And therefore, you can say, if you take, we can say it's a convolution matrix of size 5, with the first row being the vector 1, 2, 3, 4, 5, then this matrix, maybe I call it C5 is the answer of this matrix, then I can expect that this is a matrix which is invariant under these translations. So let's check. So what is the norm of inverse of T1? I'm just doing it in with C1 with T1 compared to C5. Okay, so I should say the difference. I'm using this my comp norm, but so these are really equal vectors. So let's look once more about at this vector or so. So we would say, from the point of view of or so maybe of vectors, well, if you want to know what the output is of this linear operator applied to a vector, so you would say, well, these 5 coordinates are actually values at the unit roots of order 5. And then you have to find out what the value at 0 is. So again, 0 is the first row. So mu is just the first row of this matrix here. So we have this vector. On the other hand, we know what the impulse response is. The impulse response of any vector is you take the mu applied to the flipped version and then take the value at 0. But in our case, it's just very convenient. You just take this matrix and apply it to the unit vector of the first unit vector. And you probably know what the outcome will be. It will be, okay, I wasn't making a mistake. It should be a column vector. You're getting exactly the first column. So what is the connection between the functional that you get at 0, the output at 0, which is this for any given input? So it's this linear functional 1, 2, 3, 4, 5. What is the impulse response? Well, this happens to be 1, 5, 4, 3, 2. And now you can say, well, this is a bit strange. You know what the flip operator is doing. The flip operator, one second, I have to move this bar a little bit down. Sorry. The flip operator applied to 1 to 5 is opposite order. I mean, you could also do flip left, right, and you would get this. And if you would do flip up, down, you wouldn't see anything because your row vector doesn't change if you read it upwards or downwards. So I'm using an involution operator, which is applied to this 1 to 5 vector. And that's what you really would do in the group theoretical sense. Remember, the unit roots of order 5 are points in the complex plane marked on the unit circle. And if you start with 0 and you say, I'm going backwards, you would go from 0, which is minus 0. So the first value should stay where it is. And then the last value is, of course, the first in the negative direction. So if you take this operation, then you're having the right thing done. Okay, maybe just as an experiment, Cn is 1, 5. It's a complex vector, and this vector has an involution. I'm checking what that involution is doing. And the answer is the first coordinate is the first coordinate. Maybe we see better if you take the third component, which is the same as, well, this is neutral, but now I'm 5. Yeah, I don't see on my screen, I don't see the targets completely. Maybe I make it a little bit smaller. Yeah, here is it better. So maybe the second coordinate of the involuted is exactly the last coordinate. So the second, I would say, if you're plotting it, it should be the first guy to your right. In the new version is the conjugate of the one which was to the left, which is the last coordinate. So you see it's the minus 0.110 and so on, which goes into +1. The next one, number 3, is going into minus, well, 3 is 2 to the right of the origin from 0. So you should read it coordinate number 0, 1, 2. And if you read it backwards, you have coordinates -1, -2, and so on. And again, you see it's the conjugator. So now we are looking at the vector y, which is the FFT of x. And then you're looking at FFT of involution of x. So we have taken now the conjugate combined with the group theoretical flip operator, and I've called it involution. And if you compare the values, you see it's exactly the same thing up to conjugation. The plus of the imaginary part is going to the minus. Now we also can ask, what is the norm of a vector? Maybe I'm starting again. The norm of a vector, well, I have my normalization, so it's a vector with Euclidean length 1. And now what is the norm of the Fourier transform, FFT of y? And it turns out to be 5, which I find, sorry, yeah, of course. FFT of y was nonsense. It's the Fourier transform, well, maybe, yeah, comp norm FFT of y. So we're taking the FFT of the FFT of x and x. And we see they are differing in size and in value, but if you would look closer, you would maybe, well, maybe I'll compare it. FFT of xx divided by 5 is one thing, and you take the x here. And if you look at what you have here now, is you're seeing this is exactly the flip operator. So we have the same coordinate. The first coordinate, the value at 0 doesn't change if you go to the minus, the minus index. The first to the right is the first to the left, and that's the last vector. The second one is the second last, and you see there is no conjugation. So applying the Fourier transform twice is the same as the flip operator if you normalize it. So actually my comparison was, my plan was, what is the norm of FFT of xx compared to the norm of xx? Sorry. And for sure, this is just the square root of the lengths. So sometimes I'm using fu is FFT of I of n. So that's the matrix. Oh yeah, I should maybe also tell you this, divided by the square root of n. So here, recall n is 480. And I should convince you that actually applying this Fourier matrix, so if I say you give me a random vector, maybe set, is set should be a random complex vector of size n and 1. And I'm comparing now, because I'm not sure if the normalization is correct, FFT of set, so I'm getting a column vector of size n, or I apply the Fourier matrix that I have determined by the FFT by applying to the set, and that should be the same. And yes, everything is fine. But here I was using the original matrix, the FFT of I of n, so the matrix representing. And usually people would say, well, doing a discrete Fourier transform or by matrix multiplication is a very bad idea. You really should use the algorithm. But on the other hand, we can understand a lot from using the matrix by looking at the matrix or so and understanding what it is doing. Now, the observation in the case of example of continuous integral was that the inverse Fourier transform is more or less the same, but with a plus in the exponent. So let's try to see what happens if you multiply f with, we compare the matrix with its transpose matrix. So is the matrix symmetric in the real sense? And the answer is yes, the matrix has same size and indistinguishable number. So you can do it by looking at values for small size or so, but for n equals 480, the difference is at least noticeable, but it's still, remember, it's the numerical precision of MATLAB that pops up here somehow. Okay, so that means when you're taking the matrix and you do the conjugation, it's actually just the same as the prime, and we compare it now with the identity matrix. And what you observe is this is the identity matrix, only what you have here is the amplification by n. And so I would say it's more intuitive, recall that I was saying the normalized version of the Fourier transform to understand it from a linear algebra point of view, not from a point of view of actual discrete Fourier transform. That will the Fourier transform matrix is better, but from the linear algebra point of view, the unitary version, so it's just a renormalization, is better. Clearly, the norm of any vector x compared to the norm of fu with x. Okay, it should apply to the column vector. What's going on? Oh yeah, I think that was too short, yeah. So I should take a random vector, maybe complex valued vector x now, and then I can do this. I can apply it. This is the norm preserving version of the Fourier transform. But what I wanted to show you is that this matrix is really a unitary matrix. So that's the kind of the secret of discrete Fourier analysis, and also the starting point for Fourier series theory. So yeah, it's not norm, it's comp norm. So I will do it once more so that you can see it. Okay, so what I'm experimentally checking is take the unitary version, so the Fourier version of the unitary matrix, and then you will see that it's the same as the unit matrix. Of course, you can change the order, and as we have seen, taking the transpose conjugate, which is what MATLAB is doing when you do the prime, you really get just the inverse matrix. So what does it mean that the matrix is having these vectors? And that means that in the first case, you're saying, of course, now I'm doing once more, I take a random vector, column vector of length n. So of course it means that if you apply the matrix fu with fu prime to the vector x, maybe the comp norm, I'm getting my vector back. That's not surprising. But what you know from general associativity of matrix multiplication, you can either say I'm forming, which is very cumbersome, matrix multiplication, FU with FU prime, or I'm doing first matrix multiplication on the vector and then another matrix multiplication. Kind of, this is a side remark or so. You see, it's done in a different way, and if you would do it timing, I'm not sure if we can, maybe you can try it to do this. Maybe I'm doing M is a random matrix of size 4000, and I don't know, U is a random vector of size 4001, and then I'm saying take M with UU. Talk. I'm doing it twice, or I'm saying you're doing it as MATLAB would do it. I see it's significantly slower. And of course, what MATLAB is doing actually is it's doing it in the way that it says, well, I get a matrix, and then I get another matrix, so therefore I have to do matrix multiplication, and then the product matrix is applied to the vector. And we all know that matrix vector multiplication requires n scalar products. Matrix multiplication requires n squared scalar products. So if we have 4,000 of them, there's a big difference between n and n squared such scalar products. So that's why the traditional matrix multiplication in MATLAB is much slower than the one that you would do by applying on a row vector right matrix multiplication. So that's one of the harmless reasons why I prefer to work with row vectors, because I mean, for me, signals are, if you look at signals, I see a row vector horizontally in front of myself. Therefore, I'm using myself in most of my experiments row vectors with the right matrix multiplication, but it has the side effect of being even a bit faster or so. So what is the point here? That I was telling you, if you compare the vector with the original vector, we have the same vector. But what does it mean if you are doing first matrix multiplication with the transpose conjugate? Well, you have to think of the matrix FU as a collection of vectors. And these vectors, rows and columns are more or less the same, are put, you take the first column, for example, which is actually, of course, constant 1, and then you're transposing it. So you're taking a scalar product of x with the first, with the second, and so on. And then you're synthesizing, you're taking linear combination with these coefficients. So essentially, you could say COF is FU prime with XX, which means we're doing Fourier analysis. We're having those pure frequencies, and I don't want to start looking at the plots, but you should, of course, look at the plots of these pure frequencies, and you will see exactly that the first one is constant 1, the second one has 1 period, the second one has 2 periods, and so on. And so the FU prime with XX is the normalized version of taking the Fourier coefficients or taking coefficients. And the second thing is to do the synthesis. On the other hand, what does it tell you if you're saying FU prime with FU is the same as I of n? Now you're taking all the columns of your matrix FU, and you're taking scalar products with all the other columns of this. Remember, the rows of FU prime are the conjugate of the columns of FU, but now appearing as row vectors. What is matrix multiplication? You pair rows with columns, and the ones which are appearing as rows are conjugates. So really, you're taking scalar products in this way. So this is simply the Gram matrix. So it's a Gram matrix of size matrix It's Fu prime and it's Fu. And what we have seen here is the Gram matrix of a system of column vectors is the identity matrix. And what does it mean? The scalar product of any two vectors is just 1 in the normalized case, so it would be n in the case of ordinary Fourier transform matrix, and you have 0 otherwise. That means you have all these orthogonality relationships. So that's kind of one of the secrets that we're getting. Now, I would like to mention that there is also a command in MATLAB already, which produces more or less in the same way as I put my conf map. So I would say HGFei or so is the convolution matrix of size with input vector 1 to 7 would be exactly the same as the gallery MATLAB circulant matrix or so. Now also to T1 is wrought by unit matrix of size 7 to have a compatible by 1. And now I'm saying, let's compare this matrix GF. What was it? I'm not sure now. Yeah, it was GF. And compare it with the matrix, or maybe I'm just saying this with T1, with GF. And then you see this circulant matrix is doing a good job, but also the norm of, maybe I'm doing FGF, F is, no, I should first define the Fourier transform matrix. So we have FFT of I of 7. So this is the matrix corresponding to the Fourier transform. Now I'm checking whether FGF7 or so is we are conjugating this convolution matrix with the inverse with the Fourier transform matrix. So kind of we are looking at the matrix, the linear operator, which is given by the matrix in the Fourier basis. That's the same thing. So we are multiplying F7 with GF with F7 prime. And that looks like a matrix which is only concentrated on the diagonal, and that's actually true. So you know how to look at the matrix. So what was the name of the matrix? This was, this was FGF. So I say, is it a diagonal matrix? So I take the diagonal matrix made out of the diagonal of this FGF7 and compare it with the original matrix. So the matrix is a diagonal matrix if there is outcome what size equal and error is in the order of numerical precision or so. And then of course you can say, well, what is the diagonal of FGF7? This is a certain vector, but we can also look at the FFT of the generating vector, which is this here. Well, now it's a bit strange, but maybe, no, I think we should, I have to take it in the opposite order. Yeah, okay, you see, there was, well, yeah, I have to check it where there's something, probably some normalization or so that I was, so essentially, of course, what I was expecting, and I have to correct it, I would expect that done correctly, I would get that it's a diagonal matrix which corresponds exactly to the to the Fourier transform of the input convolution matrix. Yeah, probably, let me just play around. It's involve of 1 to 7. But it doesn't matter. Okay, so I will save this and correct it in the diary or so. So I think this is more or less all I wanted to show you with some MATLAB experiments. And again, I would ask you whether, okay, now after this MATLAB experiment, so this would be an approach telling you I can get a lot of expectation about what the Fourier transform should do. And if it should be one-to-one, it should be a diagonalizing thing, it should turn a convolution operator in a multiplication operator or so. But we have seen that in the case of continuous variables, we need function spaces. And once, quite a while ago, more than maybe 15 years ago, students were complaining that I'm using so many function spaces. And so finally, I have developed a collection of symbols. This is maybe the first real encounter with this collection of symbols, which you will see, and which should help you to get an idea of how all these function spaces are related to each other, which one is bigger and which is smaller, why you would like to use a new one, and how it's related to the given ones. And it's all kind of like children garden. They would say, yes, this is a circle, this is a square or so. So in this sense, I would like to spend a few minutes to show you in the first way what my symbols are. So if I would start with the integration theory, I would say the Lebesgue space of an integrable function is the blue object. I call it L1. Now, all the norms that we are using for function spaces with the continuous integral can be also done in a discrete way. So what is the L1 norm in Rn? And then you would say, okay, I'm taking the sum of all the absolute values of all the coordinates. So that would be absolute value of x1 plus absolute value of x2, and so on. So in the xy plane, the unit ball would consist of all the elements with absolute x plus absolute y less than 1. And kind of this was the first idea. I'm using the unit ball of this Banach space with respect to the norm as a symbol. But then the other idea was, if you come later on with spectrograms, you would plot signals in the time frequency plane. And then you will see that taking the Fourier transform in the time frequency plane is the same as a rotation by 90 degrees. So if I would take the ordinary unit ball of the L1 space, you would have a Caro pattern. Rotating it by 90 degrees would be a Caro pattern again. And then you will say, oh yeah, it's fine. The Fourier transform leaves L1 invariant. And I must say, no, that's one of the troubles. If integrability of the Fourier transform guarantees that you can use Lebesgue integration to do the Fourier transform, you are getting to the red domain, which is, we can already say it's according to the definition of the Fourier transform domain, all the functions having this integral representation. And we will use this rotated symbol. So rotation by 90 degrees should be Fourier transform or so. Now, we also know that the set of all the vectors in the plane who have norm less than 1, the unit ball in the Euclidean sense is this circle. And the point is you can rotate the circle in any direction, and of course also by multiples of 90 degrees, you will get exactly the same space. So later on I will tell you there is even something like a fractional Fourier transform. You rotate by any angle and you will always get the same space, and that's L2. So Plascher's theorem is one of the things that you can read off from this nice shape of L2. We have not introduced L2, but of course in the Lebesgue sense it's the space of measurable absolutely continuous functions. So if you're going to understand Planchar's theorem, you're saying, well, I know that the Fourier transform is well defined on L2, and it's an automorphism. It's norm-preserving, scalar product preserving, a one-to-one mapping. The inverse Fourier transform is fine. And then I'm saying yes and no. It's like calculating with real numbers. You can multiply with pi. Every element, including pi, has an inverse. So pi times 1 over pi equal 1. But you have to be careful. It's not through integration. If you would try to say, I'm starting with a function in L1, and I would like to do the inversion again with this integral transformation Fourier transform, I have to be in the subspace of all functions from L1, which also have a Fourier transform in L1. And because of the symmetry between forward and inverse Fourier transform, you can say you have to take a function which is inside the intersection of the two spaces. So you take the blue symbol and the red symbol, and in order to compare all of them, I made this plot on the right-hand side, below, lower, the combined plot. So you see there are elements which are functions which are in L1, but do not have a Fourier transform in L1. So they are, let's say, they are not even in L2, but maybe we stay inside the yellow domain, a function in L2, which is in L1, but the Fourier transform is not in L1. This sounds like a terrible abstract situation, but it is not. Just take a box function, a rectangular graph. Then that function will be integrable. If you square it, it will still be very simply Riemann integrable. But if you take a look at the Fourier transform of this, you get this well-known sinc function. The sinc function is the function which is sinus pi x divided over pi x. And I also will show you a little bit at another time how to understand the behavior of the sinc function. But this function is decaying only like 1 over x, and 1 over x is a function which has an infinite integral. So it's related to the harmonic series, the sum over 1 over n. And if you take 1 over 5 plus 1 over 6 plus 1 over 7 plus 1 over 8, you're getting 4 copies of something which is at least 1 over 8. So you get together 1/2. If you start with 1 over 65 until 1 over 128, you get 64 copies of something which is at least the size of 1 over 128. So you're getting 1/2 as many times as you want, and the same is of course true when you do the integral from 1 over x from 1 to a large number. You get arbitrary big area. So the box function I would place it here. The sinc function, of course, is in the red domain. It's a Fourier transform. It's not integrable, unfortunately. So we're outside of the blue domain. We're square integrable because if you take 1 over x, if you square it, it decays like 1 over x squared. That's great. We're inside. So we have very nice properties. So it's kind of, for me, already unavoidable if you want to deal with the function spaces to introduce the statement that I have already made, that the Fourier transform is inside C0. Now C0 corresponds to the subnorm. If you take the subnorm in the plane, in the complex plane, you're getting the maximum's norm. Maximum in the plane is maximum of absolute x and maximum of and absolute y. So what is the unit ball in the complex plane? It's just the rectangle which goes from -1 to +1 in both real and imaginary part. Again, you would expect that that the symbol should be a square, but if you rotate the square, you would kind of pretend that it's Fourier invariant, and that's why I choose this symbol. Of course, the dimensions of this green symbol representing C0 is made such that the Fourier algebra, all the Fourier transform of L1 functions, but L1 is closed under convolution, so L1 with L1 is in L1, even bounded measures with L1 are in L1. Therefore, we are saying the Fourier transforms of L1 functions, if you multiply them, they're again in the same space. So it's why they are a pointwise algebra, and that's why I talk about the Fourier algebra. So we have this situation. And of course, the dimension of the green box was chosen that if somebody would give me an element which is both in the green box and in the blue area, so you give me an integrable function which is bounded, and I claim that then the function would be square integrable, which is quite easy, because what is the square of a function? Well, it's at most the absolute value of the function times the maximum of the function, and you can pull it out. So a bounded integrable function must be square integrable. In terms of my plot, there are, if you take the intersection of the green rectangle with the blue rhomb, you're inside a yellow area or so. And so in this way, I tried to kind of make a catalog of symbols, which is good enough such that if you see how the symbols are related to each other, in this way of pictures, you can get an idea of how these function spaces are related to each other. So for example, in the traditional course on Fourier analysis, I would use the inversion theorem for the functions which are in L1, but also in the Fourier algebra, which is the same as saying the Fourier transform is in L1. So the yellow domain is in this case, and I probably should stop here. Now, this is just another picture of the same situation. I will tell you, and maybe that's the beginning of the next lesson, that in some areas it's better to use the Wiener algebra, so kind of subspace of the green, both the integrable functions and the bounded functions. So this black object is inside of everything we have seen so far, except it's not inside the Fourier algebra, because if you take the black object, which I will describe in detail, and rotate it by 90 degrees, of course you're inside, you start inside the blue object, then you must be inside the yellow object or so. Everything is now inside, I mean, the new objects are inside the yellow domain. And the good thing is here you can use Riemann integrals to do the Fourier inversion theorem, but still it's not the final goal or so. But maybe I stop here by saying, well, the next goal will be to do Fourier inversion, but using only Riemann integrals on the intersection of this Wiener algebra with its Fourier transform. So we are having a situation, I'm not sure if the next picture is, yeah, no, kind of, it's not, I mean, this is just to tell you that I have a lot of pictures, and probably I should just stop, yeah, maybe the goal will be, I will try to produce a picture which is a very nice test space, which is as good as the L2 space, and then we will take the dual space, which I will call the space of mild distributions, and that will contain the Dirac combs, and the Dirac combs will have a Fourier transform, we will have a Fourier convolution theorem and all these things. So by making our space a little bit smaller, plus Fourier invariant, we get a good basis, which is, well, not a replacement for the Laurent-Schwarz theory, but for engineering applications and for digital signal processing, a simplified version of distribution theory. And I think with this outlook, I should stop now my today's presentation and see you next time.